Hi, my name is IGriess, and I am a junior studying biomedical and electrical engineering at CSU. Today I will be applying the concepts I learned in ECE 312, 332, and 342 to the signal transmission part of a radio system. The red box contains the block diagram for the signal transmission part of the radio system. In this block diagram, we have a signal from A, usually a voice or audio signal, being amplified, then multiplied with a carrier frequency sinusoidal signal from the local oscillator, or LO. Then the signal is run through a power amplifier through a bandpass filter to ensure it remains within the given frequency range, and then it is sent out to the antenna. I'm going to begin by applying the concepts I've learned in ECE 342 to explain why mixing the signal is necessary. Then I'll look at the mixer and bandpass filter from an ECE 312 perspective. After that, I'll use 332 to explain the circuits that are used to create this system. And finally, I'll briefly look at the antenna from the perspective of ECE 342. For a signal to be transmitted into the air, an antenna must be on the same order as the wavelength. For example, if we wanted to transmit a voice signal at 3 kHz through the air, we can use the equation lambda equals c over f, where lambda is the wavelength, c is the speed of light, and f is the frequency. Solving this equation with a frequency of 3 kHz, we find that the wavelength is 100 kilometers. In order to transmit this, we would need an antenna several kilometers long. So therefore we need to use a mixer, because higher frequencies can use much smaller antennas. If we were to shift the 3 kHz signal up to 1 GHz, our wavelength is only 300 meters, so our antenna would only need to be several meters long. Now let's briefly look at the different types of modulation used for transmitting signals. There are two main types of modulation: amplitude modulation and frequency modulation. Amplitude modulation, or AM, multiplies the carrier signal with the input signal, getting the result shown in the graph. Frequency modulation, or FM, shifts the frequency of the carrier signal using the input signal. Amplitude modulation is the type used in our block diagram. The diagram shows the Fourier transform of the original signal and the Fourier transform of the amplitude modulated signal. The bandwidth of the original signal is shifted up to the carrier signal, so that the bandwidth is now placed around the carrier signal frequency. Let's take a look at the bandpass filter from the perspective of ECE 312. To do this, we will obtain the body plots of the transfer functions of the filters. This is the body plot for the transform, 1 over 1 plus st to the n. The three lines correspond to different values of n. This is the transfer function of a low-pass filter. N corresponds to the number of stages in the filter. As n increases, the magnitude and phase decrease at a higher rate. Now this is the body plot for the same transfer function, but I've replaced s with 1 over s. This is the transfer function for a high-pass filter. By putting these two filters in series, we get a bandpass filter with a body diagram that looks something like this. Now let's look at the circuits which may be used to create this system, starting with the circuit that is used in the local oscillator. Ideally, this circuit is a parallel LC circuit. The ideal LC tank doesn't take into account energy dissipation, though. Because wires produce resistance, there is always a resistance in the circuit. This circuit causes oscillations because the circuit oscillates between storing energy magnetically in the inductor and electrically in the capacitor. Because the real LC tank dissipates energy, the tank needs to be refilled. The tank can be refilled with the transistor circuit circled in the figure. In order to change the bandwidth of a local oscillator, we can put multiple transistors and capacitors in parallel, where the transistors simply act as switches. Now let's look at the circuit for the mixer. We could, in theory, convert the carrier and input signals to digital, then mix them together, and then convert that back to analog. But usually carrier signals in cell phones or 1 gigahertz or higher, so you would have to sample at 2 gigahertz to convert the carrier signal to digital. This is very expensive to do, so instead we just use a single transistor. We just use a transistor, like the one in the diagram, to mix the two analog signals together. This single transistor does the mixing, amplifies the signal, and the LC load of the circuit works as a filter. So the amplifier, mixer, and bandpass filter from the block diagram are all contained in this single circuit. But there is one problem with this circuit. It is not good practice to add the three signals together by putting them in series, because connecting transistor circuits in series breaks the circuits. One way we can combine these is by using a transformer. The magnetic fields from the three input signals would be used to induce an output signal at the transformer output. But this is not how they are combined in a cell phone. It is a much more complex circuit which we will not be covering. Finally, let's take a look at the antenna. The diagram shows the radiation pattern of a dipole antenna. With this type of antenna, the sending and receiving antennas have to be on the same axis. So if the sending antenna is pointed up, the receiving antenna has to be pointed either up or down in order to receive the best signal. So this would not work very well on a cell phone. In a cell phone, our antenna has to be omnidirectional, small, cheap, and efficient. One way this can be accomplished is by using multiple dipole antennas in order to create a more spherical radiation pattern. So in conclusion, we looked at the signal transmission part of a radio circuit. Using this, we can transmit many different types of data, even multiple voices, at the same time, and we can transmit without using very large antennas. This portion of the radio circuit is incredibly important because it is used in our cell phones, computers, radios, and many of our other electronics.